After narrowing down what's going to be on your test, I made the review sheet, and then from the review sheet, I put together this set of PowerPoint slides. Now, there are quite a few slides, but I am going to post these slides on Canvas. So, first question, or I'm looking at your review sheet, it says, what are the differences between the terrestrial and the Jovian planets? I've got this little pointer here. Let's see if it's going to work for me. Oh, there it is. Okay. So down here, okay, there are the terrestrial planets and the Jovian planets. Okay, so generally kind of know the difference between them. Then we talked about the formation of our solar system. And remember that we kind of talked about, stars give a nebula, and then that nebula, our nebula was called the solar nebula, and the sun turned on and planets kind of formed in the disk, in the plane of the ecliptic around our sun. So generally know when we talk about galactic recycling, oh my goodness, when we talk about galactic recycling, what we're doing is talking about stars that are giving their material back for new stars to be born. So the nebular theory then is specifically the formation of our sun and the planets in our solar system. So there are several terms associated with the formation of our solar system, the nebular theory. So for instance, here's the solar nebula right here. Let's see, what else do we have? We see the word condensation, okay, material coming out of its gaseous state, and planetismals, it's a baby planet, okay. So I can kind of see some terms. I'm reading condensation, planetismals, frost line. This talks about the frost line. We talked about the frost line is between what two planets? Hopefully you would say Mars and Jupiter. And over here I see on your test is going to be a question about within the solar nebula we had hydrogen and helium gas, hydrogen compounds, rock, and metals. And you can see by far the most abundant was the hydrogen and helium in the solar nebula. The term accretion is a cool one. Accretion means, in the case of the formation of planets, it just simply means kind of the planet getting larger and larger with the material that's, I like to think of it as like a snowball getting larger and larger with the material it runs into. So how do I say this? The sun, which is in the center here, actually the pressure and temperature increased, and we're going to see with this in other stars too, until nuclear fusion began in its core. It began pumping out large amounts of energy via thermal nuclear fusion, and that's when we say the sun turned on. And then with the sun turning on, we had, of course, hopefully say is solar wind. All right. Then we're on to our first of our terrestrial planets. In all of the planets, I need you to know generally what they look like. So if I were to ask you a question, and I don't see it on here, I think it might be associated with this. No? Well, if I were to ask you a question about the appearance of Mercury, for instance, hopefully you'd say it closely looks kind of like the moon. But I kind of jumped the gun. I have a few general questions about terrestrial planets. When we talk about geological activity, let's see, there it is, geologically active, if there is still liquid mantle in its center, liquid magma in its center, or somewhere beyond the crust. The three regions of or three parts of a terrestrial planet: core, mantle, and crust. Very good. Now, generally, I want you to, let's see, geologically active. Which ones are geologically active? So, of course, the Earth is geologically active. I'm having a hard time finding my pointer. The Earth is geologically active. Venus is geologically active. Mars, maybe, maybe not. And Mercury and the Moon is geologically dead. And I kind of likened that to isolating a piece of pizza. It cools off a lot faster. And then you don't have that liquid, and then it becomes geologically inactive. Very good. So I kind of got ahead of myself. Hopefully you would kind of say this sort of looks like the moon, but actually this is the surface not of the moon, but of Mercury. Mercury, of course, is the planet closest to the sun. Let's see, what else do I have here? So I started to say also with regard to all the planets, if I were to show you a photo of Mercury, hopefully you would pick it out in a lineup. So you're going to have a planet lineup. That's a PowerPoint slide presentation going to be kind of playing on a loop during your test, so you'll answer those questions. Let's see, a scarp on Mercury. All right, so here is a scarp on Mercury. It's kind of a cliff sort of region, and the big thing that I want you to know is, there it is, cooling. Actually, other planets, other objects have this sort of kind of cliff thing we call a scarp, and it is from the planet or the object cooling. Let's see, what else do we have? Speaking of cooling, or hot or cold, Mercury, even though it's closest to the sun, its nighttime temperature is just amazingly cold. So on night, it's going to be negative 173 degrees Celsius. And the reason for that is that it rotates so slowly, slow rotation. Remember, I think I talked about that in lecture. Its slow rotation gives its crazy cold nighttime temperature, and it's got a pretty hot daytime temperature. But actually, if you compare this hot temperature, I'm thinking it's not, I think it might be even a little cooler than Venus, and Mercury doesn't have much of an atmosphere. That's kind of the deal between Mercury and Venus. Speaking of Venus, we move on to Venus, and I did pick a picture about, I thought this is kind of cool. These are actually kind of crater remnants, okay, and there's a feature on Venus that they call Miss Piggy. I thought that was kind of cool. I started to mention before, but I'll go ahead and say it here, that I want you to be able to, let's see if it's on, trying to see what picture took this. Oh, I guess it's not going to see that. I'm not going to go back to it, but in one of the pictures of Mercury, the surface of Mercury, I could have underlined that it said that the spacecraft Mariner, the Mariner mission, actually orbited Mercury for a long time and took some great pictures. And so I'm wanting you to kind of get a sense for the spacecraft associated with each planet. Spacecraft associated with this planet is, I think, is this Venera? Venera 13 spacecraft. Of course, hopefully you'd say that's from the Soviet Union. And it's interesting that Venus actually, as far as I know, has only been landed on one time by this spacecraft. I think that is so interesting. So Venus, the thing about Venus is we don't see the surface. We said that you can map it using radar imagery, but the Venus's atmosphere is very thick. It's got a precipitation cycle that includes liquid sulfuric acid, H2SO4, that's sulfuric acid. In its atmosphere, it has a lot of CO2, you would tell me is carbon dioxide. And that actually then is what gives it a very solid warming effect. The CO2 acts as a blanket. I have a picture coming up in a minute to look at the greenhouse effect. Yeah, greenhouse effect. So the greenhouse effect can work on all sorts of different objects, all sorts of different planets. And what happens is light can come in through the clouds. It interacts with the surface heats up, and then that heat actually is not able to escape from the material that's in the clouds. And one of the things that can trap thermal energy is carbon dioxide, and Venus has its fair share of carbon dioxide. All right. Another thing I see listed here is retrograde rotation. Know what that means. So on Venus, its retrograde rotation means that actually it spins on its axis backwards. And I know in Unit 1 we said it's all about counterclockwise. And all the planets do orbit the sun counterclockwise. And most of them spin counterclockwise on their axis as you're looking down at their north poles, except for Venus. Venus spins clockwise. And the reason for this is they think it got hit early on. And there you go. That was the last thing about Venus. Then we move on to Mars. And I list some on your review sheet, some rovers and spacecraft associated with Mars. One of the rovers that is gone to its resting place in the sky. No, Spirit actually, remember, I think I told you, got stuck and it missed its cycle to get its solar panels energized, and it's just kind of dormant now. Maybe, 200, 300 years from now, somebody will go and wake it up. But anyway, Spirit, here's a picture of Spirit. And other things, I'll just kind of read from your Opportunity was another spacecraft. Viking was another spacecraft. Curiosity is still sending back pictures, so is Opportunity. Pathfinder, Phoenix, okay. On Mars, one of the things I put on your exam was this humongous volcano. Actually, it's I want to say caldera, a volcano caldera. It's just humongous, covers about the size of Missouri, and it's called Olympus Mons. One of the questions I have on there was that, I think I have these a little bit out of order, but features suggesting past liquid water on the Martian surface. So hopefully you can kind of see this erosion that running water has caused. And then kind of related to that, if this isn't a very good picture, I don't think. Oh, maybe this is better. These little tributaries, again, running water. Okay, so that's kind of evidence, those channels, that water once flowed on the surface of Mars. Now, evidence for liquid water on Mars surface currently, actually, I don't know if you can kind of see these dark streaks. Because those dark streaks, we can take pictures now, we can take pictures later, and they're going to actually, the dark streaks are going to change, and that's due most likely to liquid water running. Evidence for water on Mars. This is similar. We can kind of see some different features here that that suggest, or changing features that suggest that surface water is running. Oh, I see that I missed an image of something about the polar ice caps. Polar ice caps, you should know that on Mars that there is some solid water, but also there is some solid CO2 at the poles. All right, so now on to historic suggestion of intelligent life on Mars. So Mars actually has these kind of dust features. Okay, and they're seasonal, and so it's not unusual that we kind of see these things kind of come and go. But what Schiaparelli said is he could see what appeared to be these kind of things that might be canals, like the Panama Canal, as in humanly made. Okay, so that was kind of a suggestion that there might be life on Mars, even without visiting it. General appearance of Mars, to me, Mars looks like kind of different places here on Earth. It has this sort of red material going here, and that's due to the presence of iron or iron oxide. All right, then the last one is Mars has 2 moons. Earth has one big beautiful moon, and then Mars is the only other terrestrial planet to have moons and has a pair of them, but they are probably captured moons. They look like potatoes. So you're going to want to know the names of these moons are Panic, Phobos, and Deimos. Panic and fear. I think that's what that stands for. Okay, then on to the Jovian planets. So the first Jovian planet is Jupiter. So one of the features about Jupiter that's been around 300 years plus is this great red spot. This, by the way, remember, is a Europa. One of the Galilean moons is actually casting a shadow. But anyway, so great red spot associated with Jupiter. How big is Jupiter? Oh, here's also another great red spot picture. It's so beautiful. How big is Jupiter? Well, you're going to want to know these 4 facts about how big Jupiter is, and I'll leave those to you to kind of check out. This with regard, I'll go ahead and say them right quick. With regard to its mass, Jupiter's 318 times more massive. With regard to Jupiter's mass and the rest of the 8 planets, rest of the other 7 planets, Jupiter is 2.5 times more massive than all the other planets combined. Jupiter, volume-wise, could contain 1,300 Earths. And if we wanted to have a second sun in our solar system, Jupiter would have had to have had 75 times the mass it has in order to reach an object that could become a star. So one of the things, again, with regard to spacecraft, I want you to know Galileo, this probe, actually fell through the clouds of Jupiter and gave us some great information. Also, I'm looking at my notes here. Yeah, that's all I have here. So Jupiter has kind of these striped kind of features around off the equator on either north and south direction. So they are called belts and zones. And looks like I should have, yep. So this should be belts. No, wait, belts are warmer. Yeah, and zones are warmer material, while zones are darker in color and cooler material. Oh, no, I guess this should be zones. Zones are lighter in color. Final answer. Goodness gracious. Zones. But one of the things I want you to know for your test, and I'm sorry, my writing utensil's not very good right now, but with regard to those belts and zones, that they go back, like they alternate the direction that they go, and we call that differential rotation. So that's also on your review sheet, and so will be on your test. Differential rotation, kind of going north and south from the equator. We have bands that go one way, the next band goes the other way, and the next band goes the other way. They kind of alternate going parallel with the equator. Okay, very good. Now we get on to Saturn, and some of us saw Saturn through a telescope this semester. So raise your hand if you did. So anyway, these, of course, Saturn has some beautiful rings. And one of the things about the rings is they from Earth's perspective, the tilt will appear different over the years. So that's kind of my thing there. We're kind of got a nice tilt going on right now. The next thing I have listed is that I have spacecraft probe, the Voyager mission that was a flyby, and the Cassini mission, which just only recently, and this I think talks about it, the Cassini spacecraft recently actually went ahead and fell to its doom into the planet Saturn. Let's see. So there's no exam question this semester about the major divisions, which just kind of slipped my mind. But there are these major divisions, the Cassini division, the Encke gap. But I do have a question about the F ring. So I think this is so cool. The F ring actually is held in place by a pair of moons, Pandora and Prometheus, that kind of keep that material in line. I just think that is so cool, so amazing. They call them shepherd satellites. Remember that another name for the moons that orbit the planets other than the Earth are satellites. Okay, and then I kind of finish up, and this isn't the best picture. I showed you some better pictures in class about this kind of six-sided feature. We're looking down from the North Pole at Saturn, and it's just a hexagonal kind of pattern that the clouds make in the planet. I think that's so cool. So on to Uranus and Neptune. Let's see. Uranus and Neptune, they both have rings, and they both have moons. All of the Jovian planets have rings and moons. I have on here that that I want you to know something about the way that Uranus's rings were found. So that's kind of what you're seeing here. Okay, this is Uranus. Okay, and one of the cool things about Uranus is that its axis of rotation, what lies basically in the plane of the ecliptic. So what happened was, as Earth orbited the sun's over here, and of course Uranus is orbiting the sun too, but it's going a lot slower. This star, looking at the star, actually the star's light was blocked out at various times as the Earth changed in its position relative to the rings. The ring material blocked out the star. That's called occultation. And so this is the light curve down here. Uranus, again, you can kind of see Uranus's tilted axis of rotation. It lies about, 3 degrees outside the plane of the ecliptic. So it has some crazy seasons. So if I were to ask you about its seasons, you might want to say something about, as we move clockwise across the diagram, we see every 21 years it gets a new season. So 21 times 4 is how long it takes to complete one orbit. Now, I could not find this in my slides, but I have it in my review sheet. This is Neptune, and this is Neptune's great dark spot. So you're just going to have to take my word for it. It was one of the interesting facts I know that we saw on the video. So that's the great dark spot of Neptune. Let's see. Then one last thing about Neptune. Actually, Neptune is our outermost planet, and Neptune was found because Uranus was doing something funky in its orbit, and following Newton's laws of orbital motion, it would suggest that there was something beyond Uranus, and it was Neptune. Isn't that cool? So then I have a few questions here about the moons that orbit the Jovian planets. They are so cool. If we're going to go visit something, and we have visited Titan, one of the moons around Saturn, if we're going to find life out there, it might not be on another planet. It might be on one of the moons of the Jovian planets. So I have on your review sheet, I want you to generally know Io, Ganymede, Callisto, and Europa. Okay, the 4 Galilean moons. Here's Io. I have a couple slides on Io. I want you to know the general pockmarked appearance of Io. It's got this sort of kind of coughs up volcanic material, sulfur-containing compounds. That's why it's so yellow. And then the other thing about Io, the closest moon to Jupiter, is that it goes through this, it's called tidal heating, and it's similar to if you were to take a stress ball and kind of squeeze it, let go, squeeze it, let go, squeeze it, let go. You're actually energizing the molecules in it, and then they'll get warm. So that's what happens as Jupiter bumps up or comes in the vicinity of a nearby large moon. It kind of squashes out, and then it squeezes in, squashes out, squeezes in, and that's how it gets its heating. It's called tidal heating. Then I have, so that was Io, and now here's Titan. So Titan, I mentioned, is a space place where actually we have landed. It's one of the many moons around Saturn, and Titan has a cycle of liquid, but it's not water. It's actually methane or ethane liquid, and actually has oceans. In terms of, I can see on your review sheet, I'll just put the letter H here. I think it might be on the next slide. But the spacecraft Huygens actually landed on Titan. So these are some images of Cassini. And Cassini then actually, like I said, Cassini must have carried the rover, Huygens, and that actually landed on Titan and transmitted data. Isn't that cool? And then we go on to Enceladus, which is also orbits the planet Saturn. And Enceladus, the cool thing about Enceladus, it's got these tiger stripes. But the other thing is that we have seen, these are photographs of Enceladus. We've seen these geysers of, so that must be liquid water under that crust, and then it freezes as it jets out of the planet. Isn't that cool? So that's Enceladus. And then I finish up by a moon around Neptune. Neptune has a moon called Triton, and it has this kind of cool looking surface. It looks like a cantaloupe. Okay, so here's also then here on the, this is all Triton. So Triton is got that cantaloupe feature kind of surface around Triton is a moon that orbits Neptune. All right. So then we go on to electromagnetic radiation, and we've been talking about the different cousins. Okay, so this is most energetic, and we have least energetic over there on the right. So you're going to want to know the order of these cousins. Okay, there are actually 6 by my count, kind of kicking out cosmic rays. So know their general energies. Let's see, what else did I write down here? Relative order, relative energy, wavelengths, and frequency. So hopefully you would say this is the short wavelength, but it's got a high frequency. Remember, frequency is the number of cycles per second that cross a point. So over here on the right, and with radio waves, we have long wavelength and we have a low frequency. So we have a big, long wavelength and a low frequency. Let's see. All right. And then I brought in one more slide. This down here you might find helpful. For every wavelength, for every energy, every form of electromagnetic radiation, if you take its wavelength, which is lambda, times its frequency, you will get the speed of light. Okay, onto black bodies and black body radiation. So this bar is acting like a black body, and kind of the light it's oozing out would be its black body radiation. And we can see from left to right two things, hopefully. You see the dominant color getting shorter and shorter wavelength, and then you also see it increasing in its intensity. So those are the two laws of electromagnetic radiation. So let's see what else I have here. I think that might about do it. So what we can do for an object is create a curve of that object. We can create the black body radiation that object is emitting. And from left to right down here along the x-axis, we have short wavelengths, most energetic, and over here we have long wavelengths. And so you can kind of see the black line is, and then kind of in the dab kind of here to the left here is the visible light. And we talked about Roy G. Biv, right? So you're going to want to kind of probably know that. That's an order also. So two things you see here. You see that the cooler it is, the more the peak is to the left or to the red. And the warmer it is, the peak is more the cooler it is, the peak is to the right, the red, and the warmer it is, the peak is to the left, the blue. So that's what will appear. And the other thing is you can see the height of the peak changes too. For the highest temperature, the peak is taller, which means it is higher. It's got greater intensity. So that is Stefan Boltzmann's and Wien's law. Okay, then we have these three spectra. Now this is the all colors of the rainbow. This is no lines, continuous spectrum. And then we talked about actually the electrons around the atoms in material that is in its gaseous state actually. They can be excited, and as they are excited, when they fall back down, they create these bright line spectra. Okay, and as they are excited, they take energies that are they take out energies in the continuous spectrum and make these dark line spectra or absorption spectra. Okay, so those are the continuous absorption spectrum and dark line spectrum. So then I have general question on there about which of the three subatomic particles causes spectral lines, and hopefully you're going to say dun dun dun, the electrons. So it's not meant to be a complicated question. Then we talked about the Doppler effect, and kind of from left to right, and here we see no Doppler effect. Okay, no Doppler effect here. And here we see the train that is emitting a sound moving from the left to the right. And it does so, it squishes these wavelengths for this observer, creates a blue Doppler effect, Doppler shift, and this over here where it's receding from, it creates a lengthen or red shift. Okay, so generally know those. Then we move on to our last part when we talked about telescopes. Three reasons we might use telescopes was to make things appear brighter, to be able to see details in objects and see objects at greater distances. There are two types of telescopes, and you've seen them hopefully both this semester so far. We have the type of telescope that uses mirrors, a reflector, and the type of telescope that uses lenses, a refractor. When we talk about angular resolution, we're talking about the detail that we can see using our telescope. And in this case, the smaller the better. The smaller between the kind of chunks of items we see, then we're seeing a sharper image. I've also got a question on there about either active optics or adaptive optics. So active optics is where the entire mirror will change. The entire mirror, where'd it go? The entire mirror will go ahead and change its angle a little bit to go ahead and compensate for differences in temperatures. Adaptive optics are more sophisticated, where the mirror actually reshapes. Okay, and to me, when we saw those kind of segmented mirrors, I can actually see that happening. So adaptive optics or active optics. We talked about different types of telescopes out there, ones that dial to shorter wavelengths and ones that dial to longer wavelengths. And actually in radio astronomy, we're looking at relatively large or long wavelengths. So since they're so long, in order to get a fix on the repeating unit, a lot of times we have to use the technique called interferometry. So in interferometry, we have multiple telescopes that are gathering, looking at the same object, and then we combine those that information to get a picture of the object we're looking at. Twinkling effect is actually kind of, if you're using a telescope on the Earth's surface, you're always going to have the potential for what we call a twinkling effect. And twinkling is caused by basically at upper elevations, I guess usually upper elevations, we have warm air and cool air kind of moving in blobs, so alternating warm, cool, warm, cool, warm, cool. And what happens is that as light passes through warm air, it will pass differently than if it passes through cool air. So then the light is bent or refracted as it changes temperatures like that. So we said that that if somebody generally uses the term seeing, the seeing is good. That means actually the twinkling, that the skies are steady. We must not have blobs of air that are kind of alternating to give us a twinkling effect. So there you go. Then last but not least, I have some pictures from the Spitzer Space Telescope right here. And Spitzer is not visible, but Spitzer is IR or infrared. And so I just kind of throw that out there. Must be a question about Spitzer on there. Now, infrared, I mentioned that because I kind of said the Hubble Space Telescope is visible, right? That's one of our coolest telescopes up there right now that's orbiting the Earth. Spitzer orbits the Earth. And actually, we're going to have the James Webb Space Telescope going in orbit about the Earth next fall. And that is also going to be in the infrared region of the electromagnetic spectrum. It should be awesome.